So first thing, do we have any question for the class? Any question for homework, assignment, or anything? Let me know. Any question from you?
I'm good.
Okay.
Yeah, with the pseudo code, you said you would cover that a little bit.
I will. Okay, so here's the thing. I will correct some of the common mistake in the pseudocode here. So first, if you look on this one here, what do you think? What this program here is? Do we find anything that you feel that is not correct with this program? What do you think? If you look on this one, sorry, I have not shared my screen yet, right?
All right, we got it.
Okay. So if you look on this one, what do you think? What's wrong with this program here? Yeah. Anything wrong with this program?
It's missing a quotation mark at the end.
Sorry, say again.
It's missing a quotation mark at the end of tip.
This one?
Is this the one that's just supposed to calculate the tip and not the total plus the tip?
Yeah, right. So the first thing is always, if you remember about the program development life cycle, right? The first thing is analyze, and in that you have to specify what is expected output here. So in this one, they asking you for the tip only. It's not the total, right? So the output here is not correct when you write out. And also, if you look on this one, here's the thing you have to remember. Whenever you're working with the program here, you always have to consistent with the variable name here. So what do you think? If you have declared the meal price here, actually you have one slot in the memory, and it's the name here, meal price. Right? And if you declare tip, also you have one more slot in the memory, it is tip here. Okay, now you enter the meal price, so you input the meal price. So after that, you enter 100 here, so we have 100 here, right? So now we move to the calculation. You set the tip here. You see, the tip here is the t here is in the lowercase. So actually, it creates one more variable here. It is tip here. It's not the same with the tip. This one the t in capital, right? So after this one, after the calculation and assignment here, you have 15 with this one. Now, when you write down, total is meal price, the meal price 100 here, plus tip. It reference to the tip here, you have nothing in that one. So actually for this one, if you work in the program, you have the syntax error here. You got it? You see the tip here is totally different with the tip here. All right, so the one thing in the programming, you always have to remember that you must be always consistent with the variable name here. You guys got it?
Yep.
Okay, so for this one also, you have declares interest at float. Float, here's some of the grammar here. I don't care about much fast. This one, enter principal, enter the rate, enter the time here. You see, the time here also is not the same as the time here. The time here is not the same as the time here. So the interest here also is not the same with the interest here. So that's the thing I want you to have to keep in mind, that you must be always consistent with the variable name here. So what is, let me see, what is this one? This one good, right? This one is, okay, so for this one also, it's quite good. It do everything is correctly. It's declare variable here and input here. You do with the calculation here, good. But what do you think? How was the output here? Anything wrong with the output? What do you think?
You also have to output the interest.
Yeah, right. For this one, if you look in the requirement, let me open the Python sort here. Yeah, so for this one, actually, they require you to print out both of the interest and the total value. That's why you have to print out the both of the interest and the print out here. And sorry, and final value here. Okay, so you see the requirement here. Write program to compute and display investment, total interest, and the final value, right? So for this one, you have to identify in the analyze in analysis step is that you have to print out both of the interest and the final value here, not only the final value, right? So for this one, you see you are missing print out the interest here. So how about this one? What do you think about this one here?
You're supposed to add plus, like right after the like the closing, what's it called? Quotation mark.
Yeah, I understand that. So this one, the declare here good, right? The input here is good.
Yeah.
Calculation here is good, but the output here, what thing? The output here is when you have everything in the text in the double quote mark here, actually is the print out amount of tip is. That's all, right? You have nothing left.
Mm-hmm.
Yeah, so actually in order to print out the value of the tip here, you have to put it here, the variable tip here, right? That's the thing. Yeah.
Yes.
Okay. And what is this? Okay, so here's one thing about this one also. What do you think? What about this one?
So again, like last time, for both outputs, you need to add plus, plus
Interest.
whatever variable.
Okay, so this you have to write down into it here.
Yep.
And final value here, right?
Yes.
But the input also is not good, right? The input here is not good, right? So remember, for every input, you need one prompt, right? So normally for the structure of the input here, you also have to use the right here, and you have to tell user what you have to do, right? So say for this one, you enter original amount. Invested. So for this one, it's a prompt, right? It's print out in the screen and to tell the user what he have to do. After that, you have to use the keyword here and input here. And input here, after that, you have to use the variable name here. You cannot this one, right? You cannot do this one. It's not, all of them is not correct here. All of them not correct. So for this one, say you have the input here and you have principal here. And you do the same. You do the same with when you are asking the user to enter the rate and enter the time here. Okay. And remember one thing about the output here. Whenever we want to print it out, what is interest or what's the final value, you always have to add it to reference to the memory here, right? So it's a memory. It is a variable name here. Okay, so I think that's all. Some of the, this one is very simple here. This one also, this one I understand that you want to do some with the command here, right? To tell what's the purpose of the step here. But if you're working on this one, the structure, the syntax is not correct. The syntax, this one correct here, this one correct here, this one correct here. But if you want to put some command here, only for the pseudocode, you have to working with this one, and you have to get the price of the meal here. So when you put everything after this one, actually when you execute program, it will ignore this one here. And the purpose of the command here is only helpful for the developer, for the software engineer to understand what is the meaning of this coding here, and what is the purpose of this one. So we think about if you have a very complicated software, you have a lot of the coding here. So when you have when you're looking at the command, it's very helpful for you to understand what is going on here and what's coming next here. Right? And I think that we will study about the command later on the chapter 3 here. Okay, so basically that's all for the pseudocode. Normally for pseudocode, user understand that you have 4 steps. You have to declare the own variable use, right? So in order to know what are the variable, you have to stick to the analyze step here. You have to figure out what is expected, what are the expected outputs, and from the expected output, you know what are the input here, right? So we also have to identify what is the data type of the variable here. It can be integer, can be string, can be character, float, or something like that. Right? So that's first step is always declare here, declare variable. And in order to know which are the variable, you have to go with everything with the figure it out the output and input here. And the second one, you have to do everything with the input. Right? So in order to with the input, you have to write the prompt and you store it into the variable here. And the next one is everything with the calculation here, assignment calculation. You have to keyword the set here. And the last one is write out the output here. So we have, when working with the output, normally you have to use a concatenation between the text and the variable name here. Any question for the homework here? Let me know.
I'm good.
Okay.
Yeah, I'm fine.
So if you don't have any question, let me move to the chapter 2 here. It's the data representation. So yes, first thing we're talking about the decimal and binary representation. And normally all of the number you use normally use the decimal system here. Decimal system, decimal means that decimal is 10 here. So we see each of the digit, you have the 10 possible value, right? So everything from 0 to 9, that means you have the 10 possible value here. And it is the 10 at the base. But actually the number system can use any base. And for the computer, it works with the binary system here. It's by 2. It's by 2 because each of the digit, you only have the 2 possible value is the 1 and 0 only. That is the binary. That's why it's by 2 here. And some of the other systems, they can use a base 8 or the base 16 here. The base 16, you have the hexadecimal. That means you have the 16 here. Okay, so we're talking about basis and exponent, right? So normally if you look on this one, for this one, you have the base here is the base 10 and the exponent here is the 2, right? So basically when you have the 10 raised to the power 2, you have 10 times 10 here. It's 100 here. Or if you have the 5, you have a 5 raised to the power 6, actually you have 5 times 5 times 5 times 5 times 5 times 5, 6 times here, right? And one thing about the exception here, so whenever you have non-zero number, it's raised to the power of 0, it's always number 1 here. So we see this one is number 1, this one number 1, and this one number 1 here. And the second exception here, that 0 raised to the power of 0 is undefined. And so if every number is not 0, when it raised to the power of 0, you always have the number 1 here. Okay, so if you look on the decimal system, normally you have a lot of column here, right? So the first column, you have the 10 here. You see, you have the 10 here is the base. You have the 10 here is the base because each of the digit you have the 10 possibility here, 0 to 9. That's why you have the base 10. And the first column, you have the 10 raised to 0, you have 1. The second column, you have 10 raised to 1, you have 10. The third column, you have 10 raised to 2, you have 100, 1,000, 10,000, 100,000, and so on. And you see, this one is this column here is the column 1, column 10, 100, 1,000, 10,000, and so on here. Okay, so use the expanded notation. So for this one, right, so you think about you have the 6,825 here. Actually, it is combination of the it is a combination of the 1 column, of the 10 column, of the 100 column, and the of the 1,000 column here. So if you look on this one, you have the 6, 8, 2, 5. So actually, it is a combination of the 6,000 here, right? You have the 6,000. This one 6,000. You have 800 here. You have 8 times 100 here, and you have 2 of the 10 here, and you have to have 5 here. And when we sum it up together, you have 6,825. Right. Okay, so for the binary system, the way it works is the same. The only difference is that the base here is not 10, but the base here is 2 here, right? Because each of the digit, you only have 2 possible here. Possibility here is 0 and 1, right? 0 and 1. So if you look on the binary system, the way it works the same. The only difference here is the base. It's not the base 10 anymore. Base 2, base 2, base 2, base 2 here, right? So now if you look on the first column, you see whenever you have 2 raised to 0, you have number 1. 2 raised to 1, you have 2. 2 raised to 2, that means 2 times 2, you have 4. 2 raised to 3, that means you have 2 times 2 times 2, you have 8. And now double it, you have 16. Double it, you have 32, 64, and 128 here. So you see, if you have 1 byte, that means you have 1 byte, you have 8 bits here. So you see the bit number 0 and the bit number 7 here. In total, you have the 8 bits here. Right? And in order to convert from the binary to the decimal, it's very simple. Right? To think about, if you have 1 byte is a 0, and have 1, 1, 1, 0, 1, 0, and 1. So now you just times them together and sum it up together. Right? So we see you have 128, you have time 1, you have 128 here. This one you have 0 here. This one you have 32 here. This one you have 16, you have 0, you have 4, you have 0, and you have 1. And the last thing, you just sum them up together, right? You just sum them up together. So we see this one you have 160, 176, 180, and 181 here. Okay? That is the way you convert from the binary to system here. You guys got it? It's very simple, right?
Yep.
Okay. So here, if I have example here, I have 0, 1, 1, 0, 0, 1, 1, and 0 here. So what do you think? What is the decimal for this one? So what do you think? What is the
on the screen?
102.
102? Okay. Yes, so this one you have 0, 64, 32, 0, 0, you have 4, you have 2, and here's 0. Add them together, right? So this one you have 96, 100, and 102 here, right? So 102 is the correct answer here. Now, so what happened if you want to convert from the decimal to the binary here? So think about if you want to convert the number 175 to the binary. So how it work here? So normally you see that if you want to convert it to 1 byte, you need the 8 bit here, right? You need it. So you have the bit number 1, sorry, bit number 0, 1, 2, 3, 4, 5, 6, and 7 here. And you know that value for this column here, 1, 2, double with 4, 8, 16, 32, 64, and 128 here. Here. So how it work here? You always starting from the left to the right. Right? So we always have starting from the left to the right. So now you have 175. You compare it with the 128 here. So whenever this one is greater than this one, you put the number 1 here. Right? So when you already have the number 1 here, actually you already have 128 here. right? So you have to minus it to 128. So you have 7 left and you have 47 left here. All right. So now move to the left. You have 47 here, less than 64. So whenever you have less than, you put the number 0 here. All right. So you now still have the 47. You move to the left, you have 32 here, 47 greater than 32, you put the number 1. So when you have number 1 here, you only have the 32 here, right? So you have to minus it to 32 here. You
It's
have
15.
Yeah, you have 15 left. You move to the right, you move to the right. So you see the 15 here, less than 16, you have put number 0 here. Move to the right, you have 8 here, 15 greater than 8, you put the number 1 here. You only have 8 here, so you have to minus 8. You have 7 left, move to the right, greater than 4, you have 1 here, 4 here, minus 4. So you have 3 left, right? You have a 3 left. You move to the right, you have 3 greater than 1, you put number 1 here. So we already have 2 here, minus 2, and you have 1 left. And 1 left here, perfectly match with this one here. All right. So now you see, if you want to convert from 175 to the binary, you have 1 0 1 0 1 1 1 and 1 here. Okay. That is the way you convert from the decimal to the binary system here. But actually, I don't require you to do it by yourself. You can use the calculator if you want. So if you were using the calculator, you can go to the programmer here, right? So think about this one. If you want to convert the decimal number 175 here, 175 here, you see you have binary of 1 0 1 0 1 1 1 1 here. Okay. Any question for this one? Let me know.
I'm good.
Oh.
Okay. Okay, so that's the way you convert from the decimal to the number to the binary, and from the binary to the decimal here. Okay, that's all. Okay, so now we move to the hexadecimal system. The hexa, that means you have this for each of the digits, you have the 16 possible value here. Everything from 0 to 9. That means from 0 to 9, you already have the 10, right? And for the 10, and the next one, you have A, you have B, you have C, you have D, you have E and F here. So when you think A is the same with the decimal number 10, same with the 11 here, same with the 12 here, same with 13 here, 14 here, and 15 here. All right, see, everything from 0 to F, that means the same with everything from 0 to 15. So everything from 0 to 15, actually you have the 16 possibility. Right? So if you think about the hexadecimal system, for each of the digits, it can be everything from 0 to 9, A, B, C, D, or F here. Okay. Okay, so the way it works is the same with the decimal and the binary also, right? So when you break it down into the column, you see here, when you break it down in the column, you see, instead of the base 10 or instead of base 2, now it has the base 16, right? Because each of the digits, you have the 16 possibility here. That's why you have base 16 here, base 16, base 16, and base 16 here, right? And the first column is the 16 raised to 0, it's always number 1. 16 raised to 1, you have 16. 16 raised to 2, you have 16 times 16. You have the 256 here. And this one, 16 raised to 3, you have 4,096 here, and this one you have 65,536 here. Okay. So now, what happened here? Sorry. If I want to convert from hexadecimal to the decimal, it works the same, right? So we think about if I have the number of the 2b here. So what do we think? If I have the 2b in the hexadecimal, what is the decimal value of that? Okay, so now remember everything about the hexadecimal, right? You have everything from 0 to 9. After that, you have A, you have B, you have C, you have D, and E here. E and F here, sorry, E and F here. A is a 10, B is 11. So actually for B here, you know that you have 11 for this one. you have 11 for this one. And for 2 here, you raise to 16, you have the 32, right? 11 times 1, you have 11. So for this one, you have the 32 in this column, and you have 11 in this column. When you add them together, 32 plus 11 here, you have 43. Right? So now you can see by converting from the 2b in the 16, so in the hexadecimal system, you can convert it into the 43 in the decimal here. Okay, this one is 16 base and this one 10 base. You guys got it?
Yep.
Okay. So now let me give you another example here. So if I have kind of C and 4 here, what do you think? If I have C4 in hexadecimal, what is the decimal here?
Wait, C is 12, right?
Yes, A 10, B 11, C 12. Yeah, C 12.
Well, 12 times 16 is 192.
And plus 4, right? So we have 196.
196. Yeah.
Yes, or you can use the calculator also, you see. So basically, if you have here, you have hexadecimal. You click on hexadecimal, you have, what is it? C4, right? C4. Oh, sorry, you have C4. You have C4. So when you convert to decimal, you see, you have 196 here. Okay? That's the way you convert it. Oh, sorry. Okay, so if you look on the hexadecimal digit, you remember that each of them, they have the 16 possibility here, everything from 0 to 9, and A and B and C and D and F here. Okay, so now what's the thing? First one you convert from decimal to hexa here, right? Yeah, the example here I give you is that when we want to convert from the hexa to decimal, and now if we want to convert from the decimal to hexa, the process is in the reverse way. Yeah, the process is in the reverse way. So think about if you want to convert from the 23 here. So the same, you do everything from the left to the right, right? So you have a 23 here, less than 4096 here. You put a 0 here. And you move to the right, less than 256 here, you put the 0 here. Now move to the right. So in order to make up for the 23, you need one of the 16 here. That's why you put the number 1 here, right? So when you have the 1 here, actually you take 16 from that. So you have 23, you minus 16 here, you have 7 left. Now we move to the right, you have 7 left. That means you need the number 7 here, right? So you see, if you want to convert from the decimal number 23 to hexadecimal, you have 17 here, right? You have 17 here in hexadecimal. The same with this one. If you want to convert from the 875 from the decimal to hexa, you do everything from the left to the right. You have 0 here, right? So you have 175, 3 of the 256 in order to make up for the 875 here, right? 4 is not, 4 is too much, and 2 is very, very small here, right? So that's why you have the 3 here. Now, when you need the number 3, you see you have 875, you divide by 256, you have the 3 and remaining here, right? So now you need that, you know that you need 3 of the 256. So you have this 107 left, and in order to, you move to the right, right? So in order to make up for the 16 here, you need 6 of them. You need 6 of them. You see 107, 0.7, you divide by 16, you have the 6 and remaining 11 here, right? So we have the 6 of the 16 here. Now you have remaining, it's 11 here. In the 11 is, when you convert it to the hexadecimal, you have number B here. That's why you have B here, right? So now you see, if you want to convert from the 875 in decimal, you convert it to hexadecimal, you have the 3, 6, and B here. It's quite straightforward, right? Any question for that?
Good.
Okay. Okay, so you can using the hexadecimal notation. You see, if you have 0, 1, and 7 and 9 here, you can convert it to binary here, or decimal here. You see, from 0 to 9, the hexadecimal is the same with the decimal here. But when you move to the number 10 in decimal, you have A, you have 11, you have B, and so on here. Okay, so now if you want to using the hexadecimal notation, when you if you want to convert from the binary to the hexadecimal here, remember that you only have the group of the 4 digits together, right? Because you know that if you have 4 digits, if you have 4 binary digit, so basically you have 2 raised to 4, you have the 16 possibility, right? So that's why for one hexadecimal, you only need 4 binary digit. If you look on this one, for one hexa digit, you need the 4 binary digit here. Right? You only need 4 binary digit in order to represent one hexadecimal here. So you only have to group every 4 bit together, and you have to work in from the right to the left here. You have to working from the right to the left. So for this one here, you see, you want to break it down. See, it's the first group here, the second group here, the third group here, and the fourth group here, right? So now you convert it to this one here. This one, if you have all of them number 1, you have F here, right? And you have 0 for this one. You have 0 for this one. This one, you have 1, 0, 1, 0 here, and you're looking 1, 0, 1, 0 here. You have number A here, right? You have number A here, and this one you have number E here. Okay. Now, in the case that I have another example here. I have 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1. Okay, so now if I want to convert this one to the hexadecimal, what do you think? What I have to do? Remember that you only have to working from the right to the left here and group every 4 digits together, right? So we have this one group here. You have this one group here. You have this one group here, right? So in the case that in the left, it's not enough for the 4 digit. Actually, you can add 2 more 0 here, right? So in the case that you don't have enough 4 digit, you can either add 0 at the beginning of that one to make it to the 4 digit here. Okay, so we see for this one, when you convert to the decimal, I have 1, you have 3, you have 8 here, so 11. So actually B here, right? I have B here. For this one, I have the 6 here. This one, if 8 and 4, I have 12. So I have a C here, and this one I have 2 here. So when you convert, when you convert 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1 to the hexadecimal, you have 2, C, 6, and B here. You got it?
Yep.
Now you move to the integer representation. So how computer process number, it depends on each number type, right? So basically you have a lot of the number type. It can be the integer, can be floating, can be double, a long integer. For some of the specific programming language, you have a lot of the data type here, number type here, right? And the way the integer are stored and processed in a quite different manner from the floating point number here. So the integer can be stored here. So one thing you have to remember is that the integer here, they can be stored unsigned here number. That means all the negative, non-negative. So it can be 0, 1, 2, 3, and 4, something like that. It's unsigned number. Or the signed number. The signed number, it can be positive, can be negative or 0 here. So we can have a negative 5, can be 0, can positive 10. That is the sign number. Right? And also for the floating point number, we also have a sum of the variation here. Now the first thing you're working with the unsigned here, the unsigned integer. You know that unsigned is a non-negative number, everything from 0, 1, 2, 3, something like that, right? And the whole number here. Okay, and normally the computer process information in the form of bytes. And you know, but for 1 byte, you have 8 bit here. For every 1 byte, you have 8 bit, right? So it can be stored in the 8 bit or 16 bit or the 32 bit, something like that, right? And the way it store, you see the way it store 2 digits here and stores a 6 digit here must be the same length, right? Must be the same. So in case that if you want to store in the 8 bit here, this one only have the 2 digit. So in order to do that, you have to add in 0 to the left to make it up for the 8 bit here. So in order to store this one into the 8 bit here, you have to add it to the 6 more 0 here, right? 6 more 0 to the left, and you have 1 1 here to store this one. And for this one, you have to add in 2 more 0 on the left to make it 8 bit here. Okay. And this one is called the unsigned form of the integer. It's unsigned because you don't have getting the sign here. You don't have negative here. Okay, so the way you're working with the unsigned binary integer is very simple, right? So we think about in order to store the decimal integer number 5 here in the decimal into 8-bit memory, you just convert it from the number 5 to the binary here. Right? So again, you can use the calculator if you want. I don't asking you to working manually by convert here. So you see, you have number 5 here. You see, you have the 0 1 0 here, right? Now, if you want to store it in the 8-bit memory, you have to add 5 more 0 to the left, right? So when we store it into the 8-bit memory here, you have the 1 2 3 4 5 0 to the left, and after that you have a 1 here. The same with this one. If you have 928 here, and if you want to store it into 16-bit memory, right? So you convert this one to the memory, and you have to add 0 to the left to make it up for the 16 bits here. This one here. Okay, so when you go with the definition of the overflow here, so I think if I want to store the number of the 300 here in the 8-bit location, 8-bit location here. Okay, so you can use a calculator. You see, if you want to convert from the 300 here, 300. Okay, so for the binary, you will see you have the 1 0 0 1 0 1 1 0 0 here, right? So you can write down. You have for this one actually, in order to store for 300 here, you need at least 9 bits here, right? But this case, when you convert from the 300 to the binary, you need for the 9 bit here. But for that reason, you are not able to store it in the 8-bit location here. So in the case that you don't have enough memory to store the number, they call it the overflow here. That's the definition of the overflow here. Right? So we see you have the 23 here, it's okay, right? So 23 here is okay. It's a 4-bit location. So you see, if you have the 4-bit memory location, so we have the 2 raised to 4, you have the 16 here. So you're able to store the maximum bit 15 away, because everything from 0 to 15 it's only 16, right? So the 23 here is not able to store in the 4-bit memory, and that's in that case the call is the overflow here. So overflow is the case that you don't have enough memory to store the number here. Okay, so it's a range of the unsigned integer. You have the 8-bit, you have 2 raised to 8, you have 256 value, right? So everything from 0 to 255 is the 256 here. So if you have the 16 bits, you have 2 raised to the 16, you have everything from 0 to 65,535, and you have 32 and the 64 here. Right? Okay, so remember one thing about the unsigned here. It's very simple. Just convert from the decimal to the binary, and in some cases you have to adding the leading 0 to the left here to make it up to the memory allocation here. Now we move to the size and magnitude format here. So remember one thing, the first one is unsigned integer, right? Unsigned integer here. The second one is the size and magnitude format. So the simple method to convert the decimal integer to binary work well to represent the positive and the 0 here. We also need a way to represent about the negative number, right? A negative number. And the size and magnitude format is a one way, right? Actually, you have a lot of way to represent the size integer here, and the size and magnitude format is a one way. Okay, and the left mode bit is reserved to represent the size. Remember that's the most left bit here. It reserved to present the size here, and other bit represent the magnitude here, or the absolute value of the integer. Right? Absolute value of the integer here. So here's the thing. Here's the example here. If you want to store the positive 23 in the 8-bit memory, right? So in the case of the positive, you do the same with the unsigned here. You just convert it normally. So we have when you convert 23 here to binary, you have 1 0 1 1 1 here, right? So this one is the 8-bit memory, right? 8-bit memory. That means you have 1 bit here for the size. 1 bit here for the size, and you have 7 bit here for the magnitude here. Magnitude. Okay. This one, when you convert 23 here, it only have the 5 bit, right? So in order to make up for the 7 bit of magnitude, you have to add 2 more 0 to the left here. 1 here, right? So this one is magnitude here. This one is the magnitude. And now the bit, the side bit here. So the side bit here. So whenever you have the number is a positive, you put the number 0 here. It puts the number 0 here. So whenever you see, you look on this one, actually you break it down in 2 bits, 0 here, and sorry, you break it down in 2 portions. The first portion is the left mode bit. It is the size, and the 7 bit here, 0 0 1 0 1 1 1 here is magnitude. Right? So now when you convert it, you know, when we're looking on the side here, number 0, this one is the positive here. And we convert this one to the magnitude, you have this, convert this one, you have the 23 here, right? 23 here. So if you look on 0, 0, 0, 1, 0, 1, 1, 1, 1, and you know that is a positive 23 here. Okay, so how about in the case of the negative, how it works? Again, you only have the 1 bit for the sign here, right? 1 bit for the sign and 7 bit for the magnitude here. Okay, the same with the negative 19 here, right? So in the case of negative, the side bit here always number 1. In the case of negative, the side bit here number 1. And now you take the magnitude of the 19 here. 19, you convert it to the 1 0 0 1 1 here. So we have 1 0 0 1 1 here. The 5 bit, right? This one 5 bit, and so we need 2 more 0 here on the left. So in order to convert from negative 19 to the sign and magnitude format, you will have 1 0 0 1 0 0 1 1 here. Right? You have 1 0 0 1 0 0 1 1 here. So now if you look into that again, break it down into portion. First bit here, number 1, you know that is negative. Right? The 7 bit here is the magnitude, and when you convert it to the binary, you have 19. So you see 1 0 0 1 0 0 1 1. When you convert it to the sign and magnitude format, you have negative 19 here. Okay, it makes sense. Yep. So in the case of if you want to store in the 16-bit here, right? 16-bit here, so you have to add to all of them 0 here to make it up to the 15-bit here, right? And 1 here for the size here. It makes sense.
Yes.
Okay,
Yeah.
thank you. But you have the huge problem with the sign magnitude here. Right, the sign magnitude here. That is the problem of the zero, problem zero here. So now we think about if you want to store the decimal zero here, the positive zero here, right? The positive zero here. It's the 8-bit here format, right? So if you want to convert the number decimal zero here into the sign magnitude, you will see that if you have the 8-bit memory, the 7-bit you to store the magnitude and the 1-bit to store for the sign, right? So we think about if you store about -0, so the first bit, the sign bit is number 0 here because it's a positive, right? And the magnitude here is 0, so that's why you have the 7-bit 0 here. Right? Okay, so we see all of them 8-bit here, number 0, it is a positive 0. So what happened if I had -0 here? If I had -0, you see the first one is a sign, right? The negative, that means you have number 1 here. And you have magnitude here 0, that's why you have all of them number 0 here, right? So we see in order to represent number 0, you have 2 ways to represent it. All of them 0 or 1 and 0 here. So it makes a lot of confusion with the computer here. Okay, you see, like make a lot of confusion with the computer. That's why for the computer, they normally don't use the sign magnitude here because it's very confusing when working with the number 0 here. Okay, see the number 0, you have 2 ways to represent it. This one or this one here, right? This one or this one. Okay. Now you already know that you have the first one, you have the unsigned here, right? Unsigned. The second one, size and magnitude. The third one here is a 1 complement. 1 complement here. Okay. So here's a 1 complement work. Normally it works when working with the positive number. Just do the same, right? When working with the positive number, you have 1 bit, the size is number 0 here, and the magnitude here, you just convert it normally. Right? So now think about you have positive number 6 here, right? You have positive number 6 here. So we see if you have a 4-bit location, right? You have 4-bit location. The first bit here is the sign number 0 we call it's a positive here, and the 6 here, when you convert it to the binary, you have 1 1 0 here. Right, so that the positive 6, you have 0 1 1 and 0 here. But for the negative here, you see the negative number, that is negative. That's why it's the bit here, the first leftmost bit here is number 1. But for the magnitude here, they convert everything from 1 to 0 and 0 to 1. So whenever you have 0 here, you convert it to, sorry, whenever you have 1 here, you convert it to 0. Whenever you have 1 here, you convert it to 0. And you have 0 here, you revert it to the 1 here. That is a 1 complement format here. Okay. So here's the thing: if you want to store the number -37 in the 8-bit here. So think about if you have 8-bit, the bit number 1 here is the size, only number 1 here. Right. So now we have the 7-bit left. For this one 37, you convert it to have 2, 4, and 6 here. That's why you have to enter the number 0 here. All right. So for the positive number 37 here, you have 0, you have 1, you have 0, 0, 1, 0, 1 here. And now you know that you're working the negative, right? So the first bit here is number 1, and all of them here, if you're working with 1 complement, you have to reverse them. You have to reverse them. So here from 0, you have 1, 1, you have 0, 1, 1, 0, 1 and 0 here. All right. So now you have 1 more bit is the size. So in order to store the number -37 to 1 complement here, you have 1, you have 1, you have 0, you have 1, 1, 0, 1, 0 here. This one. It makes sense?
Yes.
Okay. So now what happens if you want to represent the number 56, positive 56 in the 1 complement, in the 8-bit 1 complement here? So what do you think? What is it if you want to convert the positive 56? What is it? Get the answer for that.
So converting 56 to what?
Okay, so remember one thing about when working the positive, it working the same, right? That normally here. So the 8 bit here, you know that the positive, the first left mode bit is 0 here. Right? So now you just convert the 56. You convert the 56 here, 56, sorry, 56 here. So you will have the 0, sorry, you have 1, 1, 1, 0, 0, 0 here, right? So we have, so 56 here, 1, 1, 1, 0, 0, 0 here. You have 1, 2, 3, 4, 5, 6, right? And you know that you need a 7 bit for the magnitude here. That's why you have to add in more 0 here, right? So for the positive, negative, sorry, for the positive 56, you can represent by 0. This one is a positive, and this one is 56 here. And in total, you have 8 bit here. Okay, that is a working with the positive always the same. That converted normally here. So what happened if you want to convert it negative 56 here? What are they? What are they? Let me rewrite in the negative here. In the positive, you have 0, 0.
Be 0, 1, 1, 1, 0, 0.
Okay, so now you see, if you have negative 56, right? So the sign here is number 1, not number 0. And for this one, you just revert it. So 0 here, you have 1, you have 0, you have 0, 0, and 1, 1, and 1 here. Okay, that is the way working with the one complement here. Okay, so now I have the number here. I have the number the 0. I have a 1. I have a 1, 0, 0, 0, 0, 1. Okay. If I have number this one in the one complement here, what do you think? What is the decimal of that? What is the decimal of that?
64 plus 32 plus 1.
Yes, that's right.
That's
97, right? So we see if you look on this one, you know that this one is positive, right? And in the case positive, you just convert it normally and see this one 64, 32, and you have 1 here. So we just convert it, add them up together, you have 97 for this one. Right? You have 97 for this one. So if I have the number here, if I have number 1, you have 0, 0, 0, 1, 0, 1 here. What do you think? In the one complement here. So what is the number in the decimal? And how we do it? What is
Negative 13?
13?
Negative?
No. No. You have to do the in the reverse way, right? So here, break it down. Number 1 here, you know the negative, right? So when you know that negative and you use the one complement format, you have to revert it first. So 0 here, you have to revert to 1, 1, 1. You have 0, 0, 1, and 0 here, right? And now you have to convert this one. You have to convert this one. You have 9, you have 64, you have 32, you have 16, right? And you have 2 here. Right? So this one is 96, 96 and 16, 114, and what is it? You can convert it here. 96 and 16, 96, 16, 112, right? 112, 12. So we have 114 here. So for this one, when you convert it to the decimal, you have negative 114 here. So we got it. Remember that when you look on number 1, you know that is negative. And in the case negative, you have to do reverse it. 0 to 1, 0 to 1, 0 to 1, 1 to 0. And after that, you just convert it to the decimal. You got it?
yeah.
Okay, so here is the way you convert the one complement to decimal here. And again, you still have the problem with the 0 again. Now think about the one component here in order to store the positive number 0 here, right? So we know that in the 8-bit memory, so the first left mode bit number 0 here because it's positive, and you have 0 here because all of them 0 is a negative. You have all of them 0 here, right? 1, 2, 3, 4, 5, 6, 7 here. Right? So that is positive 0 in the one complement here. So now in the case of the negative 0 here. So what do you think? In the case of negative 0, this one is the size. You have number 1 here, right? And you see, in the case of negative, you have to revert everything. You have to revert everything from 0 to 1. So we have 1 here, you have 1 here, 1, 1, 1, 1, 1 here. Now again, you see, for number 0 here, you have two to represent it. All of them number 0 or all of them number 1 here. Again, it's very confusing for the computer here. Okay. So now you see you have unsized integer, you have the size and magnitude, you have a one complement here, but for the size and magnitude and the one complement, they all have the problem of 0 here, because for each number of 0, you have two ways to represent it. So that's why it's very, very confusing for the computer here. So normally for the computer, they're not working. It does not working with size and magnitude. It's not working with the one complement here. They come up with the idea of the two complement here, integer here. Okay, so in the case of the two complement integer, the first thing is that you remember that it working with a positive number, it's always the same. It's always the same. The left mode bit is always number 1, and the 7 bit here is just convert it to the magnitude here, to absolute value here. Right? So you see, if the number is positive, just convert it normally here. You just convert it normally and finish. If the number is negative, if the number is negative, remember that you have to convert the number to binary and find the one complement. Right? The first thing you have to convert it to the one complement first. Right? So in the case of one complement here, you have to add the number 1 to the one complement of the number here. And if the result of the have the extra bit here, that means you have overflow, and that discards the left mode bit here. Okay. So the thing about the positive is the same, very simple, just convert it normally. But for the negative, the first thing, convert it to one complement. After that, adding to number 1, and if you adding, you have overflow, you just discard the left mode bit here. Okay, so now to make it simple, okay, so here's the rule of the binary addition here. So when we have 0 and 1, you have 1 here, right? And when you have 1 and 1, actually you have 0 and you carry out 1 here. Okay, and see this one, 0, 1, you have 1, 0 and 1, you have 1 and 1 here. This one, very simple here. Right? Now for this one, you see 1 and 1, you have 0, carry out 1. Now we have 0 and 1, you have 1, and you have 1 here. Right? So that remember the rule of the adding the binary. 1 plus 0, you have 1. 1 plus 1, you have 0, and carry out 1 here. Okay, now here's the example. You find the two complement of the positive 43. Remember, for the positive, very simple. Just do the same, right? For the 43, you know that the first left mode bit is 0 here, and the 7 bit left, you just convert the 43. So when you convert 43 here, right, you have 1, 2, 3, 4, 5, 6. So we have to add one more 0. You have to add one more 0 to make it 7. That's why you have 0 here. Sorry. So for this one, you have this one here, positive, and all of them here is absolute value here, right? So the positive is very simple. The positive is very simple here. Now, in the case of the negative, the first thing you have to convert the number to binary and find the one complement here, right? You know that this one in binary here, right? And now you have to find the one complement. So in the case of one complement, you just revert everything from 0 to 1 and 1 to 0. So this one, you convert it here. You got this one, right? You have 1, 1, 0, 1, 0, 1, 0, 0 here, right? That's the first step. That the first step is convert it to one component. The second step is you adding to number one here. All right. So now from this one, you add number one, you have 0 and 1, you have 1 here, and that this one here. All right. And this one, you don't have overflow. That's why you keep the same here. So you see, if you have negative 43 here, sorry, negative 43, you convert it to the two complement. It's the 8-bit notation. You have the 1, 1, 0, 1, 0, 1, 0, 1 here. You got it?
Yeah. Yep.
Okay, so now think about you have the negative 24 here, right? The negative 24. So the first thing you see that if you have 24, when you convert it to binary, you have 1, 1, 0, 0, 0 here. And in order to make it to the 8-bit, right? The 8-bit here. So you have 3 more 0 here. This one is a positive, right? This one is positive 23. Now, the first step, you have to convert it to the one complement. So we change from 0 to 1, you have this one here. The next step is adding to 1. 1 plus 1, you have 0, carry out 1 here. 1 plus 1 again, you have 0, carry out 1 here. 1 plus 1 again, you have 0 and carry out 1 here. 0 plus 1, you have 1 here. All right, so this one here, the number here is the two complement of the 8-bit location of the negative 24 here. Okay, so now to make it simple, let me give you some of the example here. So if I have the number 0, I have 1, 1, 0, 0, 0, 1 here, 1 here. What do you think? What is a decimal number in the two complement of this number here? And how we do it? Okay, so what do you think? What is the decimal number of this one? So first thing you see, look on this one. What do you think? This one is a positive or negative?
It's negative because the first digit's a 1.
This one here, what do you think?
Oh, not that. I thought you meant the one at the bottom. Okay, that's positive.
Okay, so this one is a positive or negative?
Positive.
Positive, right? Because the sign here is number 0. So in the case positive, you just keep it a positive here, and you convert it to the absolute value here. So we have 64, 32, you have 96, right? 96, you have 2 here, you have 98, 99 here. So this one is 99. Right? So in the case of the positive, very simple. If you look the size here, 0, so that is the positive, and just convert this one to the absolute value here. Very simple for the positive here. Okay, so now if I have example, if I have 1, 1, 1, 1, 1, 1, 0, 0 here. What do you think? No,
Negative.
I make it simple here. So 4 here. I make it 1 here. Okay. So what do you think? What is the decimal number of this one? Okay, so in order to do that, you have to do on the reverse way, right? You have to do it the reverse way. This one you have no extra bit here, so you have to do it in the reverse way. The first one, if you look on this one here, right? The first one, when you look on this one, you know this one here, it is a negative number, right? Negative number. So you have to focus on the 7-bit here, on the 7-bit here. All right. So now you have to do on the reverse way. The first one, when you're adding here, now when working the reverse way, you have to minus 1 here. Right? You have to minus 1 from that. So you have to minus 1 for this one. You see, 1 minus 1, you have 0 here. You have 0 here. You have 1. You have 1. You have 1. You have 1, you have 1 here, right? And of course, this one is negative here. Now, what you have to do next? What do you think? What do you have to do next? What do you have to do next? You have to do it. You have to convert it, right? You have
You
to
have to convert.
you have to reverse it. You have to reverse it. So this one, 0. You have this. You reverse this. You have 0 here. You have 0 here. You have 0 here. You have 0 here. You have 0, and you have 1 and 1 here, and negative here, right? Of course. And when you convert this one to the absolute value, you have number 3 here. So that's why all of them here is actually it's a negative 3 in the decimal here. Okay, that's the way working with the converting here. Okay, so now why so slow? So when the two complement cannot be done, it's in the case of the overflow here, right? So we think about if you have 8 bit here, right? If you have 8 bit, so in order to represent for the in order to represent for the negative and positive, right? So you have 8 bit, so totally you have 256 value because the 2 raised to 8, you have 256. But in the case of working with with the negative and positive, actually you only have everything from negative 127 to the positive 127. So if you want to convert the negative 159 here in the 8 bit here, you are not able to do it because it will have the overflow here. Right? Because 159 here is less than negative 127. So in that case, you cannot represent on 8 bit in location. You have to represent on the 16 bit here. Okay, so now think about the 0 solution here to see if the two complement here can overcome the problem of 2 way to represent the number 0 here. So now think about this one. The first one is a negative 0 here. Sorry, positive 0 here. And you know that for the positive, that do it normally. The sign here, positive, and the absolute here, the value here, right? So for the positive value, you have all of them number 0 here. Now, for the negative 0, right? You know that the first thing, if you have negative 0, you have the 8-bit number 0 here is a positive, right? So in order to do with the complement, you convert everything to number 1. That's why you have this one is a 1 complement here. 1 complement. Now, if you look on this one here, you see when you convert it to 1 complement, you have to add number 1 to the 1 complement, right? So for this one, you have to add number 1 here. You see 1 plus 1, you have 0, carry over 1, 1 plus 1, 0, carry over 1, and so on. And you have 1 here. Right? Now we look on this one, actually you have the 9-bit only, not the 8-bit location. And in the case of the overflow, you see, in the case of the overflow here, you just discard the left mode bit. Right? Just discard the left mode bit here. So we see, when you discard this one, you have the 8-bit number 0 here, exactly the same with the positive number 0 here. So we see when working with the two complement, you are able to overcome the problem of the 2 way to represent the number 0 here. It makes sense?
Yep.
And that's why normally for the computer they use a problem. They use a way of the 2 complement here. Right? Okay, so that review about the way you represent the integer number. The first one, it is unsigned here, right? Unsigned is very simple. You just convert it normally. The second one, you have the size and magnitude here. Right? Size magnitude, that means you have 1 bit for the size, and the magnitude here is that converted normally here. The third one, you have 1 complement. So 1 complement that when you convert for the positive, the same, but for the negative, you have to convert from 0 to 1 and 1 to 0 here. And the fourth one is the 2 complement here. 2 complement is actually working from 1 complement, right? So for positive, always the same, but for the negative, working from 1 complement, adding to the number 1, and in the case that you have overflow, that discards the left most bit here. Now we move to the floating point representation. The floating point is that the number that you have both of the integer portion and you have the fractional portion here. So you think about this one, you have both of the integer part and the fractional part here. So you see 6 here is the integer, but 6.0 is floating point because you have integer and you have a fractional part here. So in order to represent a floating point number in binary, you have to divide the number into its parts. The first one is size. The first one is size. The second one is the whole number, it's the integer, and the third one is the fractional part here. So we think about you have negative 25 here. This one is the size. This one is integer, and this one is the fractional part here. Okay, so for the integer part, you have 1 bit set aside to represent the size here. And again, you have 0, it's a positive, and you have 1, you have negative here. Okay. So in order to convert the integer part to binary, you just simply convert the same way you convert the positive integer here. Right? So think about if you have a positive 625 here, you just convert the number 6 normally, or you have negative 625 also, you just convert the 6 now normally here. Normally. Okay, and the dot or the parallel here between the integer and the fractional part of the binary number will be referred as the point here. The point is where you separate between the integer part and the fractional part here. And the point here, in this case, you can call it the binary point because it breaks it down in the binary here. Right? Okay, so now if you working with the fractional part of the decimal number, you see that you see you have a lot of column, right? So we have the column 1 here, the 10 raised to 1, sorry, 10 raised to 0, 10 raised to 1, 10 raised to 2, and so on. And when working is fractional, also you have 10 raised to negative 1, 10 raised to negative 2, and 10 raised to negative 3 here, right? So think about this one. If you have the number of the 6.25, so actually you can break it down. Sorry, let me make it 56.25 here. Actually, it break it down. This one is a column 1, and this one column 10, and this one column negative 1, and this one column negative 2 here. So we see for this one you have 100 here. Sorry, you have a 10 here, and you have 1 here. This one you have 1 over 10 here, right? And this one you have 1 over 100 here. Okay, that's all. That's the same. We're working with the way you're working with the fractional here. So for this one, actually you have 5 times 10 plus 6 plus 2 times 1 over 10 and plus 5 times 1 over 100 here, right? Because you see 10 raised to minus 1, actually it's 1 over 10, right? And 2 raised to minus 2, actually 1 over 100 here. Okay, so when you break it down, the 56.25, actually you have 5 of 10, 6 here, 2 of 1 over 10, and 5 of 1 over 100 here. You got it?
Yeah.
Okay, so the way working with the binary is the same. When working the fractional part is the same. You see, if you have actually you have this one here, right? You have 2 raised to 0 here and 2 raised to 1 here. For this one, you have 1 here, and you have 2 here. But when working the fractional part, you see this one actually you have 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, 2 raised to minus 5, and 2 raised to minus 6 here. Okay. So now for this one, you see, if you have 2 raised to minus 1, actually you have 1 over 2, right? This one, you have 1 minus 4, So 1 over 4, this one you have 1 over 8, this one is 1 over 16, and this one you have 1 over 32, and this one you have 1 over 64 here. All right, so we see if you have 1 over 2, you have 0.5, 1 over 4, you have 0.25, 8, you have 0.135, and 1 over 16, you have 0.0635, and so on here. All right, so on here. So now see how if you convert the decimal fractional fraction to the binary. So the first thing you have to raise the question: how many bits are allowed for the fractional part of a given number here? That bit. So some of them they require you the 4-bit, or some of them they require you only 2 bits for fractional here. So the first thing you only have to raise the question here: how many bits in the fractional one? The second one, you create a chart here. You see that 2 raised to number -1, 2, 3, 4, and 5, and you see when you have 2 raised to -1, actually 1 over 2, you have half, you have a quarter here, you have 1 over 8 here, 1 over 16, 1 over 32 here, and so on. So here's the thing: it works the same. It works exactly the same with the way you can when working with that with the converting the decimal here. So now think about if you want to convert the number 0.60, why is it 0.65 here? Think about that one. Now you only have to working from the left to the right. You only have to working from the left to the right, right? So see, starting from the left, 0.65 greater than 0.5, you put the number 1 here. You put the number 1 here. So when you only have the number 1 here, actually you only have 0.5 for this one. That's why you have to minus 0.5 here. So when you minus 0.5, you have 0.15 left. 15 left here. So now we move to the right. 0.15 here, less than 0.25. That's why you put the number 0 here. That's why you put the number 0 here. And now you still have the 0.15. You move to the right again. 0.15 greater than this one, you put the number 1 here. You put the number 1 here, and you have to minus it over 0.125 here. Okay, so we have 0.025 left. And when I move to this one, 0.025 less than this one, you put 0 here. Okay, and now if they are requiring to using 4 digits in the fractional part, you can stop it here. You can stop it here. So in order to convert from 0.65 to the fraction part of binary, you can convert it to 0.1014 here, because they're requiring to working with only 4 digits in the fraction part here. Even that this one not 0. Okay, you got it?
Yes.
Yeah, so exactly is the same, right? It's just converted. It's just converted here. So whenever you greater than, put number 0. Whenever less than, put whenever greater than here, you put 1. Whenever less than, you put 0, and move everything from the left to the right here. Okay, so here's the example. If you want to convert from 0.4 to the 6-bit binary number, right? 6-bit here. So you have to remember that you have 1, 2, 3, 4, 5, 6 here. Now we see 0.4 less than 0.5, right? Put 0. Now move to the left. Move to the right. You have 0.4 greater than 2 or 25. That's why you put number 1 here. So when you have the 0.25, you have to minus it here, right? You have to minus it. You have 0.15 left. Move to the right. 0.15 greater than, you put number 1 here. You put the number 1 again. You have to minus it here. You have 0.25 left. 0.25 left, less than, put number 0 here. Move to the right, less than, put the number 0 here. Now move to the right, greater than, right? Greater than, put number 1. Put number 1 here. So you have the remaining here, but you can stop it here because they requiring to working with the 6-bit binary number only. So we have 1, 2, 3, 4, 5, 6 here. So in order to convert from 0.4 here in decimal, you're able to convert it to the 6-bit here, right? So we see 0.1, 2, 3, 4, 5, 6 bit here. Okay, so now for every for the floating point, you have the three part, right? You have the size, you have integer part and you have fractional part here. So if you want to store the 75.804 at the binary number, you just store it normally here, 75, store it here, right? Store 75 and 805. If you want to store in the 8-bit here, you convert it to have 1100 here. So it convert to 00 here. See, so now if you want to convert from 75.804 in the decimal to the binary, you have 101011.1100 here. Okay, so now we move to the scientific notation. One thing I have to tell that this module is everything about the data representation here. You can think it you can see that it quite a lot of the confusing and complicated here, but the thing is that for this class, this is the only module you're working with the conversion number here, and for the next module you have nothing to do with that. You have to do for the next module working with the coding, you're working with the Raptor here, and so for that reason you don't have to be you don't have anything to be afraid of that. This only the module you have to working with the conversion, not for the other module here. Now, so we move to the scientific notation. The computer normally used for many scientific application and use it often for very large or very small number here. So some of the number is very huge number. You think about the distance from the Earth to the nearest star here, and you see for this one you need for the 94-digit binary number to represent it in the computer here. And in the case of diameter of the atom, very tiny, so you need a 30-bit of binary number here. So if you think about, if you have to remember all of the 49 digit, or you have to remember all of the 30 digit here, it's very complicated for you, right? So in that case, you have to working with a scientific notation here, that you have the way to represent it way better and way shorter here. So for example, this one here, you want to work in scientific notation, you give a number, it's written the number between 1 and 9, and you multiply by the power of the 10 here. Right? So you see, the first one is always everything from 1 to 9. The first digit, everything from 1 to 9. So for this one, you have 6.8 here. This one, you have 1.5 something here. This one, you have 8 point something here, right? So the first thing in order to work in scientific notation, the first digit is always in the range from the 1 to 9 here. That's the thing you have to remember here, right? So now think about this one. Think about this one, right? So you have the first number always from 1 to 9. That's why you have to working with the 6 here. You have to point here, right? So in this case, you have to move for 1, 2, 3, 4, and 5, right? So whenever you move to the left, you have the positive number. And whenever you move to the right, you have negative number. For this one, you have 10 here, you have 1, you have 2, you have 3, you have 4, 5. You move to the left 5. That's why you time it to 10 raised to the 5 here. Right? So the same with this one. You have everything from starting from 1 to 9. That's why you have to stop it here. Right? So for this one, you have 1, you have 2, 3, 4, 5, 6, 7, 8, and 9. That's why you have this guy here and time with the 10 raised to the power of 9 here. Right? The same with this one. Now for the negative, right? So in the case you move to the right, you have to work in the negative. You think about this one, you have starting everything from 1 to 9. That's why you have to stop from this one here. You have to stop from this one. So we see you move to the 1, you move to the 2 here. When you move to the right 2, you have to time with negative 2 here. The same as this one, you have to stop it somewhere here, right? So we see you have 1, 2, 3, 4, 5. That's why you have negative 5 here. And do the same as this one, you have to stop it here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You move to the right 12. That's why you have negative 12 here. Make sense?
Yes.
Yeah.
Okay, so this is a scientific notation. The other one is an exponential notation here. So in the case of exponential notation, you do quite the same. It's quite the same, but instead of writing the 10 power here, you can use the letter E here. You can use the letter E. And again, when you move to the left, use a positive here. Move to the left, use a positive, positive, and the right, negative, negative, and negative here. So when we convert it from the exponential notation to the ordinary notation, is the same, right? So when you see you have the E and negative 4 here, you know that you have to you have to move to the right here, right? So we have to move to the right. So you have 1.7 here, right? 1.67 here. So we have negative, sorry, you have to move to the left here, right? So we see you have the 0 here, 1, 2, 3, and 4 here, right? So that's why you have the 0 here. Okay, so now we move to the base 10 normalization here. Normalized form is similar to the scientific notation. Normalized form is similar to the scientific notation, and each normalized number have the two parts. They have the scale portion and they have exponential portion here. In the scientific notation, the decimal point is moved to the first non-digit was immediately to the left of this, right? Everything. If you remember about the scientific notation, the first decimal point always is the range from 1 to 9 here, 1 to 9. You see, see everything from 1 to 9 here, right? 6.8, 1.5, 8.9, 1.5, 8.9, something like that. That is scientific notation. And in the normalized form, the decimal is moved to the first non-zero digit intermediate to the right. So the value number is always maintained here. And normalize the decimal number, after moving the decimal point, the number is multiplied by 10, right, to the whatever power is necessary to return the number of original value here. Okay, so let me give some example here. So here's the thing, we're working with a normalized decimal number here. So for this one, normally if you work in scientific notation, if you remember about scientific notation, the first digit always in the range from 1 to 9. But when working the normalized number, the first digit here is number 0, and after the point, it always every number from 1 to 9. So the thing when working the normalized decimal, you have to remember that always starting from 0 points something in the range from 1 to 9 here. Right? So for this one, you see, you have to put a 0 here. Right? You have to put a 0 here. So we see in order to do that, you have to move to 1, 2, 3. You move the 3 to the left. That's why the exponential here, number 3 here. 3. You have is a 0.3712 times 10 raised to 3 here. The same as this one, right? So we have starting from this one here. You move to the left 2. That's why you have positive 2 here. Right? For this one, you have starting from this one, right? 0 point here. So we see 1, 2, 3, and 4. Right? So we move to the right 4. You have negative 4 here, and this one. Right? This case is a normalized decimal number here, and that is for the decimal. So how it work with the binary here? How we work the normalized binary floating point here? So basically, for the normalized binary number, you also have the 3 parts here. You have the size, you have the exponential, and you have matrix here. And okay, and the matrix is a binary. It's the same with the scale portion here. You think about, you have to think about this here. You have the scale portion. You have exponential portion here. Right? You have the scale portion and exponential portion here, and the matrix here is the same with the scale portion, but it working the exists 127 system here. And let me tell you how exists 127 system work. Okay. So the exist 127 system is able to store the exponential value here. Right? You think about the number 3 here is an exponential value, right? Number 2 here is an exponential. The number -4 or number 5 here, they are exponential value here. And the exist 127 is used to store the exponential value of the normalized binary number here. Right? So we think about so in order to represent the 8-bit number in the exit 127, the first one you have to add 127 to the number here. The first thing you have to add the 127 number. Now you change it to the binary and you adding 0 to the left to make it up to the 8-bit here. Okay, so think about if I want to convert the number -4 here to the exit 127. Right, 127 here. The first thing I had to add it up to 127. So -4 plus 127, you have 123 here. All right. So now you just convert it to the 8-bit here. So for 123, you have 0 here, you have 1 here. Right. Sorry, 123. You can convert it here. 123. So you have 1 1 1 0 1 0 0 here, and remember that you only have to add number 0 to the left to make it to the 8-bit here. So when you convert it here, you have 0 1 1 1 0 1 0 0 here. Okay, so the purpose of adding to the 127 because they don't want to use a negative number in the exponential here. So we see if you have the 8-bit, right? If you have 8-bit in the size here, if you use the 8-bit in the size here, normally 8-bit in the size. So normally you have everything in the range from -127 to the positive 127 here. All right. So by adding everything to the 127, you will have everything from 0 to the 254 here. All right. So you don't have to use any negative number in the exponential value here. So here, so if you want to convert from positive 9 with the excess 127, add it to the 127, you have 136 here, and it convert it to 1. Sorry. So when you convert the 136 to binary, you have this number here. And sorry. So if you want to represent the -13 here, you just add it to the 137, you have the 114 here, and you convert to the binary, you have this number here. So when you move to the base 2 normalization here, the process is similar with the one following the normalize the number here, right? And the point is moved, but it's not moved to the first non-zero number here. And when you multiply the number by the power 2, you need to express in the original of the value Okay, and here's some rule, but to make it short, I think it's better to working with example here. So in order to normalize the binary number, you see that you only have to move, right? You have to move to the to the first non-digit, non-zero digits. That's why you always have to move to the first number one here, right? So we see for this one, you have to move it to one here, right? So when you move to the left, you have 1, 2, 3, 4 here. That's why you have to time it to 2 raised to the 4. This one is by 2, not by 10, right? Because you are working with the binary here. So that's why you time it to 2 raised to 4 here. So for this one, you have 2 raised to 4, and you time it to 1.0 and 0, 1 and 0, 1, 1, 0 here. And now, if you want to normalize this number here, right? So you want to normalize this number here. So you have to, you know that in order to normalize the binary number, you always starting with the number 1. Right? You always starting with the number 1. That's why you have to move with this one here. Right? So when you move to the to the right one number, you have -1 here. Right? You have -1 here. So remember one thing: when you normalize the binary number, you always move to the something starting 1 point something here, right? 1 point something here. So we see for this one, you have 1.0110, and for this one, you have 1.11100111 here. So we're going to single precision floating point. So you have 2 ways to working with floating point here. The first one, it can be the 32 bit. It is single precision, and the second one, you can working with you can working with the 64 bit. It is double precision here, right? Double precision. So in order to working with the single precision format, you have the one bit is the size here. That 1 bit is the size. It's stored in the single bit. So you have, if you have positive, you have 0. And if you have negative, you have number 1 here. And the exponent is stored in the 8-bit. Right? The exponent is stored in the 8-bit here. So we see if you have the 8-bit, totally you have 2 raised to 8 here. You have everything from 0 to 255 here. Right? And you have the matrix is stored in the 23-bit here. So we see when you have 23, you add with 8, you added 1 here. In total, you have the 32-bit here. Right? And for the double precision, you have the 50-bit, 52-bit at the matrix here. You have the 11-bit for the exponent, and you have 1 bit for the size. So when you add them up together, you have the 64-bit here. Okay, so here's an example when you're converting the decimal number to the single precision floating point in binary. Right? So the side bit here is always number 0 if it's a positive, and if it's negative, it's number 1 here. Now, the next step, you have to convert the number to the binary. You just convert the number to the binary. If the number here it has the integer part and fractional part, you have to convert the whole number to binary first. Right? Now, the next step, you have to normalize the number, move to the point directly to right of the first number 1 here. Actually, non-zero is the first number 1 here. And you have to count the number of places you move to the point in order to do the exponent, right? So if you move to the right, you have to work in the negative, and you move to the left, working with the positive here. Right? So when you have exponent here, you remember that you have to working with the exit 127. That means you have to add it to the 127 here, and after that you convert it to the binary. Convert it to binary in the 8-bit here, and for the matrix here, you use this one here. You use this one in the step, and when you store the normalized part of number, the number 1 to the left is discard. Right? So actually a lot of information here, but you will find it way easier when you're working with the real problem here. So here's the thing. Here's the thing here. Right? So if you want to represent the single precision floating point for the normalized number here, you have -2 raised to -9 times this one here. Right? So if you look on this one, the first one, the sign here, the sign here is negative. Right? So you know that the sign here number one. The first one, you know that the sign here number one. The second one, you have -9 here. This one is exponent, right? It's exponent here. And you know that in the exponent, you have to working with the x's 127. That's why you have the -9 here. You plug it to 127. You have 118 here. And now if you want to convert 118 to the binary, you have this guy here, right? It's this one here. Remember that you only have to adding to number 0 to the left to make it to the 8-bit here. That's why you have 0, 1, 1, 1, 0, 1, 1, 0 here, right? So now see, this one is the exponent here. This one is the side here. Now the rest of this one is here, right? This one is the rest of one, and remember that you that follow the rule here. If the discard it, if the discard where I discard it here. Yeah, you have discard the number one of the left here, right? So we just discard the number one here. So you have 0, 0, 0, 0, 1, 0, 0, 1, sorry, 0, 0, 0, 0, 1, 0, 1, 1 left, right? So this one, the 8-bit here, you have an 8-bit here. But if you're working with if you're working the single precision, right? You need the 22 bit for this one. This one only the 8-bit. So in the case of less than 23 bit here, you have to make it up to the 23 bit by adding to the right. Remember for this one, this time you're working, you have to add into the right, not the left here, right? So you see, you have this one here. This one here is the matisa, and you adding all of them 0 here to the right to make it up for the 23 here. Sorry, 23 here. This one is the exponent here, and this one is the side here. Okay, so you see, if you want to convert from -2 times 2 raised to -9 times this one into the scientific precision floating point, you have the 1 and you have the range of this one. And this one is the way you store in the computer. Right? So when the computer reads this one, the first one, you see this one is negative here. You know that this one is negative. When you see this one, you have this one here. It's a 118. Right? So when the computer knows 118, actually you have to minus it for 127. Right? So we know that this one is a 2 raised to -9 here, not positive 112, right? And for this one, you just drop it here, drop everything on the left. You keep it to the last number one here, and you have to put the number one before this one here. So you have a 1, and you keep everything here. You have 0, 0. Sorry, 0, 0, 1, 0, 1, 1 here. Okay, that is the way working with the floating point decision here. It makes sense.
Yep.
Yeah. Okay. I think that some of you find out this is quite confusing, but we got the lucky. But that is the only chapter working with the conversion here, and in the final exam or in any assignment, you don't have to working with this one here, or you don't have to working with this one here. So that is a good point of this one. And so basically that's all for this chapter. So for this chapter, you have to understand, you know how to convert from the decimal to binary, from the binary to the decimal, how to convert from for hexadecimal to binary, hexadecimal to decimal, and decimal to hexadecimal, or binary to hexadecimal here. And you study about how to represent the integer number. In order to represent the integer number, you can work with the unsized format. You can work with size and magnitude. You can work with one complement, and you can work with the two complement here. And in the case when working with the floating point, you have to break it down in two portions here, two parts. The first one is the integer part, and the second one is the fractional part here. So, okay, so let me see what you have for this week. Let me see what you have for this week. So basically for the color, it's also use the code here, right? So it's range everything from 00 to FFF here. For the white, I think it's 0 or F. I'm not really sure. You can check it up on the web here. Which one? I forgot. True. So what do you think for the second one? What do you think? Which one is it? One and two.
Is the fourth one?
One comment with the left would be the same on the side where you can get. No, it's correct. It's correct. This one here, right? The 4-bit actually, if you store the 4-bit, you only have able to store for 2 raised to 4. You have the 16 only, right? So you are able to store the number everything from 0 to 15. And this one is the overflow here, right? It has too many here. Floating point number have the which of following. What do you think?
All of these?
Yes. All of them, right? You have integer part, you have side, and you have fractional part. This one, right? In order to convert to the exist 127, remember that you have to add it to the 127 and you convert it to the binary. What is the decimal value? Use it. For this one, very simple. You can use a calculator here, right? Use it copy and in working with the hexadecimal and enter and see what is the decimal and binary here.
A to F, right?
Yeah, right. This one, if you work in the exponential notation, right? So we have to keep it point here, right? So we have to keep it point here. And you know that whenever you move left, you have to you must have the positive number here, right? So we see we have 1, 2, 3, 4, 5, 6, 7, 8. That's why this one is correct one. Oh, exponential, right? Exponential, yeah. What do you think? If you use the 12 at the bottom, how many digits?
Hmm.
Huh? What do you think?
Is
You
it
have
12?
Yes, right. So if you see, if you have decimal, that means you have 10 base. If you have binary, you have the 2 base. If you have hexa, you have 16 base. And if you use the 12 base, that means each of the digit you have the 12 possibility here. What do you think? What about this one? You see, this one is by 8, right? So the first column is 8 raised to 0, it's a 1. The second column is 8 raised to 1, it's 8. And the third column is 8 times 8 is 64, right? So basically, you have to work in with this one here. You got it?
Yes.
Yeah.
Yes. By 8, right? So everything is 8 raised to 0, 8 raised to 1, and 8 raised to 2, 8 raised to 3, something like that. So in order to convert this one to the fractional part, you have to convert this one to binary, right? And also you have 0.4, you have to convert it to the binary also. And remember that, yeah, I see. Yes. So in order to convert the fractional part, you work in this one. What do you think? What is condition here? Bigger than maximum allowed number.
Overflow?
Yes, overflow. You don't have enough to store it, right? App here. What do you think is the app here?
Is it 15?
Yeah, 15. I think this is only floating number, right? What do you think? This one is absolute, right? So we think about you have a -7 or the +7. The absolute is number 7 here. And you can ignore the sign. This one very simple here. Absolute here or magnitude. I'm not really sure about that. That one is a
Scientific.
scientific notation. This one very simple, right? What is this? I don't. This one very simple. This one very simple. The binary point, right? The binary point. This one very simple. This one simple. This one very simple, right? This one simple. I don't want to do it. This one simple. User can use a calculator to convert it here. This one complement is and two complement is. Right? So this one, the one complement is that revert everything. Right? Is that revert everything? And for the two complement, you can work it out from the one complement and you add to number one here. Oh, okay. So for this one, ask key value. That's something you have to, I think you have to look on the reading here. Oh, sorry, we still have the, this one is a Tuesday, right? So we still have the Thursday. So I think that's all for today, and I see you guys on Thursday. We're working with some more reading assignment and working with the homework also.
All right. See you
Okay.
on Thursday.
Okay,
Have a good one.
okay, see you guys on Thursday. Bye bye.
Bye-bye.